Okay, today we're going to prove that another recursive sequence is convergent. So the recursive sequence we're looking at today is defined to be as xn plus 1 equals to 2 plus xn square root. So the first two terms of the sequence are xn, x of 1 is the square root of 2, and this is x2. So just as the previous video, we're going to use the monotone convergence theorem to show that this sequence indeed converges. Now, the theorem states that any sequence that is both monotone and bounded is guaranteed to converge. So we're going to show those two properties hold for this specific sequence. So we're going to start off by showing that xn plus 1 is indeed monotoned. So we're going to use this using proof by induction. So let us define our base case. So we have our base case, and the base case is just going to be x1, which is roughly 1.4. If we take the square root of 2 is approximately 1.4. And x2, if we compute this term right here, is roughly 1.8. So at least for the first two terms, we can see that the sequence is increasing. That is, x1 is less than x2. Now, let us move on to the general case. So far we've been hinted at the sequence might be increasing. We only saw it for the first two terms, but let's see if we can prove it for all terms. So our general case is going to be the following. So xn plus 1 is greater than xn. So if we assume xn plus 1 is greater than xn, and using this assumption, we can show that this statement implies that xn plus 2 is greater than xn plus 1, then we would have shown that the sequence is indeed monotoned for all xn. So we have to somehow massage this statement, and assuming that's true, we must show that this statement must also be true. That is, this statement directly follows from this statement. Now let us write the definition of xn plus 1. So xn plus 1 is defined to be 2 plus xn square root, and xn is defined to be 2 plus xn minus 1 square root. Okay, we can add 2 to both sides, so we get 2 plus xn and 2 plus xn minus 1. And we can take the square root of both sides as well. And here we notice that this is by definition xn plus 1. That is what we've defined here. And this is our xn. And by definition then of our sequence, this entire term works out to be xn plus 2, which is greater than this entire term, which works out to be xn plus 1. And so we've just shown that this sequence is indeed monotoned for all elements in the sequence. We have shown that starting with this statement follows. All right, now let us show that xn is bounded. That xn plus 1 is bounded. Okay, so we have just shown that xn plus 1 is greater than xn. That is, the sequence is increasing. Now, for any increasing sequence, that means that the greatest element, the lowest element is the first. So, because every subsequent element is greater than the previous one. So, that trivially defines our lower bound to be xn is always greater than or equal to the square root of 2. Because we know that the first term is the square root of 2. Therefore, every subsequent term must be at least square root of 2 or greater. So that defines our lower bound. Now we must calculate our upper bound. Now, after taking the first several terms of this sequence, I've computed them, and they all seem to approach the number 2. And therefore, that might be a good candidate for our upper bound. And we can check that. So let's write this statement out explicitly. So xn is less than or equal to 2. And how can we check if it's true? Once again, we can use proof by induction. So let us define our base case. So our base case is the following. So our base case is going to be x1 is less than less than or equal to 2. And we know that it's trivially true because x1 is defined to be the square root of 2. Therefore, it must be less than or equal to 2. Now let us move on to the general case. So we assume that xn is true, that xn less than 2 is true, and we must show that this implies that xn plus 1 is less than or equal to 2. So let us see if we can figure that out. So we, once again, add 2 to both sides. So 2 plus xn is less than 2 plus 2. We get 2 plus xn is less than or equal to 4. We can square root both sides. And here, we only care about the positive square root because we have shown that the lower bound is square root of 2, so we don't care about the negative square root. So what we get, and also notice, that this is xn plus 1. So what we've shown is that xn plus 1 is indeed less than or equal to 2. Therefore, we have found an upper bound and we have a lower bound. And just to write it explicitly, xn plus 1 is strictly greater than 2 and less than or equal to 2. We don't know if it approaches 2 or if it actually equals to 2. But now we will be able to find the limit using the following technique. So recall that the limit of xn plus 1 equals to the limit of xn, and that equals some number that we don't know yet. Let's call it x. So these two limits are equal because, if you recall, the only difference between the sequence xn plus 1 and xn is that xn plus 1 does not contain the first term of the sequence. And since limits only care about the behavior of the sequence at infinity, the first term does not affect the limit, and hence both of these sequences converge to the same number, x. Now, this property is very convenient as it allows us to write the following 2 plus xn, which is our definition over here, in the following manner. We can find 2 plus x equals to x. Now, why can we write it this way? Because we know that the limit of xn is x. We know that the limit of xn plus 1, this term, is also x. So these terms must be true. And if we solve for this, so we get x squared. If we square both sides and move all terms to the one side, we get x squared minus x minus 2 equals to 0. So here we just squared both sides and moved all terms to one side. Now if we use the quadratic formula to solve for x, this will give us the value of x, and that x is our limit. That is, the sequence xn plus 1 will converge to x. All right, see you in the next video.